I made two videos on capacitors in series and parallel. So here's going to be a combination problem where we're trying to find. So actually, I should probably explain. We have these 9 capacitors, I think, where you kind of have them in an arrangement like that. And the outer ones are all C1, which is 6.9 microfarads, and out of farads, whatever. And then the 2 inner ones are 4.6 microfarads. We're going to try to find the equivalent capacitor for the whole thing. So the charge Q on the 3 nearest capacitors to the battery. 1, 2, 3. And then we're going to try to find the potential difference, the voltage between point C and D. So we're going to try to figure that out together. Try this on your own first, see how you do. Hopefully you tried. Did you try? Okay, good, you tried, right? The equivalent capacitor. So we got to break this down, and we kind of got to draw like sort of stages where we want to make. Okay, so what do I mean by that? If we take a look right here, we need to find series and parallel capacitors. These are not parallel capacitors, right? The reason they're not, even though it looks parallel, they are not parallel capacitors because they're not hooked up to the same voltage. Remember from like if we had a battery, I'm just going to draw a very simple parallel system here. What makes them parallel is that they're both hooked up to the same potential difference, the same battery. So they're both going to get supplied the same voltage. In this case, C2 is kind of connected to this capacitor and this capacitor, which is going to provide a different voltage than if it were connected to this one, right? And see, this one is connected to that one. So they're not parallel because they're not going to have the same voltage. Or they're probably not going to have the same voltage. And the same thing here, C1, these 3 capacitors are not in a series, right? Because they're, and in order to be in a series, so let me draw another kind of example here. In order to be in a series, this guy's plate needs to be connected to this guy's plate, which needs to be connected to this guy's plate. In order for each, because of the conservation of charge, and you can watch my series video on that, they need to be connected like this in order to have Q here, negative Q here, Q here, negative Q here, to have the same magnitude of charge on each plate. So these are not series, and then these 3 are not parallel, these 3 are not parallel, right? They don't have, for sure, the same voltage. What I do know is at the end here, I know they're series because I know these 3 are, well, this plate is connected to this plate, which is connected to this plate, which is connected to this plate, which is, they're all connected in a series without any other capacitors kind of in the way here. And just to confirm that they're in a series, I can be like, okay, hey, this is going to have a charge Q. I don't know what that charge is. It's not this Q. It could just have some amount of charge, right? By the time all the charge starts flowing, this is going to have some amount of charge. This is going to have negative Q. All right? And therefore, if this has negative Q, the only way it's going to have negative Q is if this has positive Q. And if that has positive Q, that's negative Q. That's the only sole connection, so this also has to have Q. So I can think it through like that as well. I can't, and that's another reason, and I don't like yapping here a little bit. I just want to make this very clear, because when I did this problem, this is the thing that confused me. What's a series and what's the parallel? I know these are not in a series, because if this one was Q, and this was negative Q, I don't know if this one is Q, right? Because I know that there needs to be a negative charge here, but you can get negative from this side, which maybe you're left off with Q1, and you can get negative from this side, which would leave a positive charge Q2, right? So in the end, you would get Q is equal to Q1 plus Q2, because that's what's supplying the charge there, right? Because of the conservation of charge. So these are not in a series. This charge is from that one. So these are just things to keep in mind if you're ever confused. But now that we know these 3 are in a series, you can kind of just go from there. So, let's our series equation for equal capacitance is C1 plus 1 over C2 plus 1 over C3 is equal to 1 over C equivalent. So I could just plug in 1 over 6.9 microfarads because they're all 3C1. But then what you notice is you're going to have 1 plus 1 over 6.9 plus 1 over 6.9 plus 1 over 6.9. You're adding through the same thing. That's just the same as 3 over 6.9, which is going to equal 1 over C equivalent. And if you take the inverse of that, you should get 2.1 microfarads is equal to C equivalent. And if you're confused about the equation, watch my video on series. It'll make sense. So the equivalent capacitor here is going to be 2.1 microfarads. If I really quickly draw in this whole thing now, it's going to take a little bit of a second here. So now if I draw this whole thing again, I just found the equivalent capacitor, 2.1. This one is 2.1 microfarads. All right. So I know these three just got replaced by this one, the equivalent capacitor. And hey, these two are in parallel. How do I know these two are in parallel? Because they're hooked up to the same potential difference. This one has, there's going to be a potential point C and D, right? So I can think about, okay, this is going to get voltage from there, this is going to get voltage from there. Hey, you had the same voltage, so these are parallel. And for parallel, it's a lot more simple. We just say CEQ is equal to C1 plus C2. Or in this case, this is C2, right, if we check our diagram. And then this we can just say 2.1, right? 2.1, and then C2 is 4.6. 2.1 plus 4.6 is... Did I mess up? Oh my god, I messed up. This is not, you might have caught, this is not 2.1, this would be 2.3. I did my math wrong in my head. This is going to be 2.3. So 2.3 plus 4.6, you get 6.9 microfarads here. So now I can replace these two with just one single capacitor, which is going to have a capacitance 6.9. And now I've reduced, so now this is kind of the equivalent capacitor for all of these, right? And then I have the equivalent capacitor for all four of these. Oh my god, I have another series. 1, 2, 3. And they're all 6.9. Well, what do I know? Well, hey, I just solved for 3 equivalent capacitors, or 3 capacitors with the same 6.9 capacitance. It's 2.3 for a series, right? I did the math right here. 6.9, 6.9, 6.9. I can just put another equivalent capacitor for all of this. And this is going to be 2.3 because I solved for that already. And guess what? Now I'm covering all of this. This is all in the equivalent capacitor. Don't mind the inner circles. It's all, this capacitor is for all of these. And then I have another parallel. And I have another parallel. This is 2.3. This is 4.6. Oh my god, I already did 2.3 plus 4.6. It's 6.9 again. So then I can get rid of this, and I can say, hey, the equivalent capacitor for now, this included, right, is going to equal 6.9. Oh my gosh, I have another series where they're all 6.9. So if I, did the math right here, I can get one equivalent capacitor for everything, which is going to be 2.3 microfarads. So the equivalent capacitor in this case would be 2.3 microfarads. Okay, now we got to find the charge on the 3 nearest capacitors. Well, let's think about this, right? In fact, let's go back to the scenario. Let's go one step back, and we can say, hey, well, we're going to take one step back where we have C1, C1. and then let's have the equivalent capacitor that we solved for originally. So the equivalent capacitor for all of these except these two. So we'll say 6.9, which we solved for. You can literally replay like 3 seconds back. I solved for that, or 30 seconds, whatever. And then from here, I just know, hey, this is not too bad. I know 6.9. This is in a series, so they're all going to have the same charge, which is pretty nice. And then I can just say, hey, Q is going to equal, C, I can say C is equal to Q over V. The only thing is that I don't know what V is, right, for one of these. So in fact, I really didn't even have to, so I didn't have to go back to 3. I don't know what V is because this is V1, V2, V3, and that all adds up to the V total. You can watch my video on series, but I can just go back, make another equivalent capacitor, which I solved for 2.3, so I didn't really have to do all of that. So then I get 2.3, I can just put it there, it doesn't really matter. And then I know the voltage is going to equal, this is the only capacitor, so it's going to be 420 volts. And then I can do C is equal to Q over V. I do CV is equal to Q. And then I can really quickly, I have my calculator here. I can do C, which is 2.3. Remember the times 10 to the negative 6 for micro. 2.3 times 10 to the negative 6 times 420 volts. And we're looking at 9.66 times 10 to the negative 4th charge, which I think, okay, wait. This is, so we have 9.6 for these two, right? The reason it's not for this one as well, so I'm going to write 9.66 times 10 to the negative 4th for C1. So I'll say, like, I don't know, C1. The reason it's not for the second one is because when we made this equivalent capacitor for this thing, this capacitor represented kind of the charge on everything, right? So because it's the Q for the equivalent capacitor for everything, and I'm only worried about C2, right? So what I can do is I can actually get now so now I can kind of unfold this one more, right? This was the equivalent capacitor for, and this gets kind of confusing, but this is really going to be the equivalent capacitor for C2, so C1. This original capacitor was the equivalent capacitor for C2 and everything else, and the C equivalent. And this one was 2.3, and this was 4.6. So what I can do now is I can say, okay, I know the total charge on this is going to be 9.66, right? Because 9.66, right, for the original 3 capacitors got to be the same. So when I, kind of expand it out again, the total has to be 9.66. In order for this to have 9.66, I'm going to get rid of that because that's kind of throwing this off here. What I can do is I can say, okay, I know these are both going to have the same voltage V. So, and that voltage V is going to be, I can actually solve for that, making the equivalent capacitor for those two once again, which is 6.9, and then I have to say, okay, 9.66 divided by, because C is equal to Q over V, so V, oh my god, this is going to be kind of a long video. Can I make a part 2? I want to make a part 2 on this. I'll just commit to it. I'll make a 20-minute long video. C is equal to Q over V, and then V is equal to Q over C. So I can make that relationship right there. In fact, I'm going to start getting rid of some of this stuff. So to figure out the voltage between these two, I basically say, hey, I would say 9.66 times 10 divided by the capacitance, and which was 6.9. And just once again, I just want to make this very clear. What I'm doing is I have this was the original, right, that we used to solve for the charge, C1, 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 but this was the equivalent capacitor for these two parallels between C2 and everything else, the C equivalent for everything else, which is 2.3. Not this C equivalent, the C equivalent for these, right? So, and then I'm just finding, I'm using this, right? I know it's 9.66 because it's a series and everything has the same charge. I know the voltage, or sorry, I don't know the voltage. I can solve for the voltage because I know the capacitance, and that's what I'm doing. So divide that by 6.9 times 10 to the negative 6, and I get 140 volts. So if there's 140 volts here, there would be 140 volts between these two each. And what we can say is then, hey, 140 volts, now I can solve for charge, because I can do C times V to get Q, and I know this C, which is 4.6, so I can do 140 times 4.6 times 10 to the negative 6. If that stuff was confusing, please let me know. I don't mean to make this confusing. You can like leave a comment if you care. So this is C1, and then for C2 it's going to be 6.44. And I checked the textbook. This is the right answer. Okay. Now the last thing is just finding the voltage between C and D. So what I can do to do that is, let me think about this. I forgot. This one I was a little bit stuck on, so I just got to think through how I would do it again. I think I'm going to want to unravel this, right, and kind of go backwards, because I want to get to C and D. So right now, right, if this is points, I don't know, A and B, then this is point A and B, which I know is 140 volts. So now what I can do is I can say, okay, this is going to be the equivalent capacitor for this, and then everything, the C equivalent for everything else. So I'm kind of going backwards here. That's really what's going on. So I'm going to say, okay, this, and then this. So this is C2, and it's getting a little messy. In fact, I'll probably just leave it. But C1, then you have C1 here, and then this is the equivalent capacitor, which at this point was C1 as well, because then everything would equal to 2.3. C1, 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 and this is just the equivalent capacitor. It just happens to equal C1 in terms of its capacitance. And I need to find the voltage right here. So what I can do is, let me think about this. Ooh, how would I do this? So I would say maybe I'm thinking, okay, I solved that there would be 140 volts for that original equivalent capacitor. So I'm guessing this and this and this would add up to 140 volts. But then they also have the same charge. Another thing I can do is kind of just go back originally to the start here, make our equivalent capacitor here, which is 2.3. So I would say the equivalent capacitor, let me draw this again. So I can make that original equivalent capacitor, and it was 2.3, and I could solve for the voltage here. It would be the same voltage. Oh wow, so I can get a little creative here. This might not be the best solution. I need to remember I found a really good solution for this. What I'm thinking, and hopefully you realize this is part of the physics process. Like I know you got to kind of think about it. What I'm thinking is, hey, this was 9.666 times 10 to the negative fourth. This was 6.44. By conservation of charge, I know this is going to be the difference between that. So if I do 9.66 minus 6.44, this should be 3.22. And in that case, if this is 3.22, these both need to add up to 3.22 as well. So, if I now make the equivalent capacitance to here, which would be 6.9, I know it would have a charge of 3.22, and and then I can solve for V because I know the capacitance, which would be 6.9, and I know it would be 3.22 charge. So I'm going to try that out. 3.22 times, so which equation I want to use? I'm solving for V, so I'm going to do Q over C. So times 10 to the negative fourth divided by 6.9 times 10 to the negative 6 here. I get 47 volts. I don't think that's right. I don't think that's right, 47 volts. Wait, no, that's not right. Right? I don't know. I might have to get back on this. If you're watching this and you got through this so far, let me know if you have an answer how you can do this. I know I do. I think it's 10.8 volts. I got 47 volts. Let me know if you can think of a way. I'm low key a little bit stuck. I did this problem like a little minute ago. I think you'd have to I would have to play around with this more. So yeah, thank you for watching. Hopefully the first two parts made a whole lot of sense. And yeah, maybe this is your homework. Do find the voltage there. Thank you.